Let's look at this next subtopic, which is the distance of a point from a plane. So if I have a point available, I'm dealing with the vectorial form here. So if I have a point available whose position vector is a bar, and I have the equation of the plane available with me, how can I find the distance of the point from the plane? So what I'll do is I'll first draw a perpendicular on this particular plane, and I'll call it M, right? So if I can get the position vector of this M, then what I will do is I will just subtract OP bar minus OM bar. So basically I'll get this vector PM and I'll take its modulus. That is all that I have to do. So I need the position vector of this. So for that, what I'll first do is I will create this line PM. How do I get this line which passes through a point and is parallel to a given vector? So what is it? So this particular line, this pink line, is passing through A bar. Fine. What is it parallel to? Do I have any data here which using which I can say it's parallel to that? Yes, this N bar, right? Because this N bar is a vector which is perpendicular to this plane, and even this pink line is perpendicular to the plane. So this is the equation of the straight line, of the line which is passing through this point A bar and is parallel to this particular normal, right? So this line will strike the plane at some point M. I'm assuming that point R bar. So I need that point R bar, right? So R bar is equals to A bar plus lambda N. This represents every point on this particular line. So I will assume that my M is equal to this. So I'll assume that my OM bar is equals to A bar plus lambda N. I need the lambda, right? Once I get the lambda, I'll put it here and I'll get the OM. So there's one thing that I can say though. This PM, if M lies on the, if M is striking the plane here, M will lie on the plane. So M must satisfy this, right? M must satisfy this. The position vector of M must, when it is put in place of R bar, it should satisfy this equation. What is the position vector of M? I'm assuming it to be this. So I'm putting that here and dotting it with N. So because R dot N is equal to D, instead of R, I'm putting the position vector of M. So I'm taking the dot product of N with that, and that is equal to D. From this, when I solve this, I'll be getting this lambda, right? I'll be getting this lambda, which I was looking, right? I was looking for this lambda. So I'll put this lambda back in this equation to get my OM, right? So this is what I've done in the next step. I put this lambda back here, A bar plus lambda N bar. Instead of lambda, which I got after solving this, I put it back here. So I got the position vector of M. But I need to subtract the position from the position vector of M. I need to subtract A, right? Then I will get PM bar. And I need the modulus of that. So that is what I've done. Mod PM is R bar minus A. R bar is the position vector of my M now. I'm subtracting A from that. So if R is equal to A plus something, R minus A will be equal to this, right? Will be equal to this quantity. And I need mod R minus A. So I'll take mod of this, right? That is what I've done here. I'm taking mod of this. And then mod N will come out separately. This mod N and mod N square will cancel. And this is the final expression that I will get. So this is the vectorial form. So if I have my equation of plane available as a vector, if I have the position vector of this point as a vector, then I can put all these quantities in this formula and I can get the length of this, basically the mod PM, the length, the distance of this point from this plane. So this pink line's length I can get, right? So obviously you don't need to remember this formula. You need to remember the procedure. You need to remember the way I found this formula. That's more helpful to you, right? So with this we are done with finding the distance of a point from a plane in the vectorial form. Let's look at the same thing in the Cartesian form now. Let us now look at the distance of a point from a plane in the Cartesian form. So the same thing, I've taken this point P. Instead of having its position vector now, I now have its coordinates x1, y1, z1. I need its distance from this plane whose equation is given by ax plus by plus cz plus d equal to 0, right? Now, I need the length of this pink line. So what I will do is, I will once again use the same concept. If I can get the coordinates of this foot of the perpendicular M, then I will use distance formula between 2 points. So basically this formula x1 minus x2 square plus under root y1 minus y2 square plus z1 minus z2 square. Right? I hope you know this formula already. 2 points having coordinates x1, y1, z1, and coordinates x2, y2, z2. So this is how you find the distance between them. So if I already have the coordinates of this, if I get the coordinates of this, I can get the distance. So to get the coordinates of this, what I will do is, I will first construct this line PM. How do I construct the line? I will write the line in the symmetric form. The line is passing through the point x1, y1, z1 and I need its drs. How do I get its drs? The line is perpendicular to the plane. The drs of the perpendicular to the plane are ABC, right? I can straight away get that from the equation. That means the drs of this line are also ABC because this line is also perpendicular to the plane. So I can write the equation of the line in the symmetric form like this. This is the line equation in the symmetric form. X minus x1 by a is equal to y minus y1 by b is equal to z minus z1 by c. From here I constructed xyz. So xyz can be written as a lambda plus x1, b lambda plus y1, c lambda plus z1. As I keep changing my lambda, I'll keep getting different points on this line. Right, I'll keep getting different points. I need that lambda for which I get this point M. How do I do that? I basically substitute, or I assume this to be the coordinates of M. Right, I assume this to be the coordinates of M. Now the thing is, M also lies on the plane. M also lies in this plane. So M must satisfy the equation of the plane. So this is my X, this is my Y, this is my Z. So instead of X, Y, Z, because M should satisfy, instead of x, I did a into a lambda plus x1, b into b lambda plus y1, c into c lambda plus z1 plus d equal to 0. Because this must satisfy the plane's equation because m lies on the plane. So from this, solving this, I got my lambda, right? I got this as my lambda. So I can obviously replace this lambda with this particular quantity. So this is minus a x1 plus b y1 plus c z1 plus d by a square plus b square plus c square. Now from here I am not calculating, I am just explaining you the steps and writing the final answer. So you can get the coordinates of x, y, z from this very easily, right? Because all that you need to do is send a that side and then add x1. So if you have x minus x1 by a is equal to lambda, you already know lambda. You can get x, a lambda plus x1, you know x1, you know lambda, you know a. So you can obviously get x, right? That's how you can get y, that's how you can get z. So you can get the coordinates of this M, x, y, z, you can get the coordinates. Once you have the coordinates, you can apply this distance formula between this point and this point. And when you apply the formula and finally simplify, you will get this as your final answer. So all that you need to remember is this. This is in the Cartesian form. So what is the shortcut to remember this? Basically, you take up this point, x1, y1, z1. You put this point in the plane, right? So if I have the equation of the plane as ax plus by plus cz plus d equal to 0, you take this x1, y1, z1, you put it here, right? So you make this ax1 plus by1 plus cz1 plus d. You take the mod around that and you divide this with this particular quantity, under root a square plus b square plus c square, right? So develop your own ways to remember this. This thing you have to remember, this formula you're required to remember because you can't go through this lengthy derivation again and again. And this formula is used in a lot of places. That's why this is an important formula. You need to remember this. You can't just rely on its derivation because the derivation is lengthy, right? So with this, we also conclude the distance of a point from a plane in its Cartesian form. Let's move on to the image of a point in a plane.